everyone. Yeah, good evening, good morning, and good afternoon. So, from different places that you are joining today with me here. So, I'm Jeevan, and I'm from Sustainable Living Lab. I do work as an AML consultant and a tech lead at Sustainable Living Lab, and I'm based out of India. So in the next 30 minutes, I'll be taking you through, my journey of building TrueRice at Sustainable Living Lab from, turning a $100 flatbed scanner into a 30-second AI quality control engine, and then transforming whatever the manual grading of rice grains into instant objective and also AI powered insight generation mechanism as well. So I'll be taking you through from the problem we saw in the rice supply chain to the design and the model choices we made and how this system is now scaling beyond rice to rice into maize, coffee, and the other crops as well. Okay, first, whatever that you are actually seeing on my screen, why this grain QC, the grain quality control is actually mattering is that rice quality actually defines, everything from pricing to trust to livelihoods. So yet, the way we test this quality of rice is hasn't evolved since decades. Today, most of the quality checks are done manually, as you can see in the image here, people do pick and choose the rice grains, and they do use vernier calipers kind of toolkits to kind of measure the length of these rice grains and stuff. So today, as I was telling, most of the quality checks are done manually and taking anywhere between 60 minutes to 120 minutes per at least 20 grams of the rice sample as well. So depending on the grader's experience, the person who is actually grading, it depends on his level of experience that he has. So the issue isn't just about the time here; it's about the inconsistency as well that is being created. So maybe let's say there are two inspectors who can grade the same lot differently, same lot of rice samples differently. So leading to a constant disputes in between the farmers or the millers or the even the exporters over what's actually premium quality or what's actually the average quality of rice. So these two kind of when that happens, the exporters will actually face exporters or the millers or the farmers will actually face delays or even even rejections from which are even the rejections from uh, the big clients that they have. So it will be worth over $1 billion annually due to mismatched grain grading standards and all these things. So this inconsistency is isn't because of lack of effort, or it's it's because of agriculture is still one of the least digitized sectors actually, and especially in the post harvest quality control. So that's exactly where AI can play a democratizing role over here. So not to replace the people, but to make their judgment faster, more fairer, and backed by the data as well. So yeah, to understand the scale of this, the scale of the problem, to know that okay, why are we solving this thing? So every single year, around 50 to 60 million metric tons of rice, is being traded globally. So every shipment, every lot, every trade agreement, relies on the one critical step, which is the quality check. And yet whatever the step this whatever the quality check step that is there remains almost entirely manual. So the problem isn't about the lack of the data here, but it's about how accessible is the digitization. So with that, the technology to analyze grains exist, but it's locked behind expensive lab setups that that small and medium sized mills can can't basically afford kind of thing, even small and medium sized exporters can also not afford those things. So the result, we ended up with a we end up with the slow, inconsistent inspections that that will cost time, money, and even the trust with the client as well. So now think about the ripple effect. Every misclassified sample, like every misclassified rice sample, whatever the lot that it is in, leads to reprocessing, again repacking it, additional transport. Once the client rejects the exported rice, that comes back to us, and even the export, whatever the export rejections will happen. So this is increasing both the financial losses and even the carbon footprint as well. So the real question became what if quality control could be as simple as scanning a document? So that's the thought. What inspired us in that inspired us to create TrueRice. So with that, yeah, let's get into the actual idea. So here's the simple idea that changed everything. It's a we used a flatbed scanner you can buy from which you can buy for under $100, which can capture high resolution images of rice grains. I will show you those images as well as we flow through, in next 5 to 10 minutes. And this is basically $100, flatbed scanner that you can use to capture these high resolution images of rice grains. And over uh, our AI model will actually analyze those images in which are having thousands of rice grains, rice kernels in seconds. So that's where there's no complex setup, no special lighting, no special calibration that we need to do, kind of thing, to scan these things, or have some proper camera lighting setup and all these things to actually capture the data and then process it and then annotate it and all. So you we did it all on this flatbed scanner. So with that, as I was telling again, there is no complex setup that we have, no special lighting that is needed, and no calibration efforts that need to be put in. You just place the grains on the scanner, click once, and within 30 seconds, the TrueRice will generate a detailed report, with metrics like grain size, uniformity, and also what are the defect ratios that these rice grains will have, all with almost up to 99.5% accuracy. So that's the best part. The most the very uh, the best part over here is the accessibility that the people are getting, the people in terms of the farmers, millers, and the exporters. So the accessibility being the core point over here. So this system doesn't need a lab or an engineer to run. So even a local farmer, cooperative, or a mill operator or an exporter can use it with minimal training. So we designed it to work a bit low internet connectivity areas as well. So with just a laptop and a scanner, as you can see on my screen, so it will making it more practical to use, and it's more plug and play AI solution that anyone can deploy. So before getting into the architecture and the design principles that we followed, first I think I'll take you what this means in numbers, what is the tangible ROI of TrueRice. So manual grading today takes about, as I was telling you, it takes about 2 hours per sample, which is let's say 25 grams or 50 grams of sample. So and whereas TrueRice does the same job in just 30 seconds. That's almost roughly 240 times faster. And even in terms of accuracy, has also jumped from 65% in manual inspections to over 97%. Meaning all the the results are not only faster but also more also far more consistent as well. And then coming to the cost wise as well, so each test now kind of costs about 20 cents instead of $2.5. If you actually have a person doing the test, maybe the person taking let's say at 30 minutes, or let's say not 30 minutes, but yeah, of course, 1 hour to 2 hours, per sample kind of thing. So this is it's almost 13 times cheaper over here with using TrueWise. So this shift allows even small and also the mid-sized mills to perform frequent quality checks, and not just one-off certifications kind of thing. So these numbers are actually building a clear case for why this system matters, and it doesn't just bring innovation, but it brings measurable uh, efficiency, accessibility, and also the trust into the supply chain of rice grains. So with that, now I'll take you through, till now we have seen the measurable impact. So let's look at why TrueRice actually works, the design principles behind it. So we built TrueRice on three engineering pillars, as you can see here. So the first is the frugal engineering. So that is coming here up with the entire system runs on a commodity hardware. So it's like a basic flatbed scanner and a consumer grade GPUs, let's say RTX 4090 or RTX 5050, whatever we have it on our now we have it on our NVIDIA RTX graphic cards on our AI PCs, or the personal laptops that we are using. So there is no specialized imaging devices, or or cloud GPUs that the TrueRice as a product is using. So this is actually keeping the cost very minimal, while ensuring anyone, even a local corporate farmer or a miller or exporter, can actually can run the AI model to analyze whatever the scan that is coming out of the scanner. And secondly, this is also about the human-centered AI that is coming out here. The goal was to make AI trustable. So every detection, which is coming out of comes with the visual explainability overlays and the confidence metrics. I'll be demoing that in our product as well in next 5 to 10 minutes, showing the users why the model labeled a kernel as a broken one or a chalky one. So this helps inspectors verify and trust the AI output, rather than treating it as a black box model kind of thing. And third, also comes with the scalable architecture. So the entire pipeline is kind of modular, and that means basically the same backbone model can be fine tuned for maize, coffee, dal, or any type of other grains by retraining just the classification layers. And this design, it's keeping it. This modular design is basically keeping the scaling costs also quite low, while speeding up the adaptation across crops and other geographics as well. So at its core, these are the principles, ensure that AI in agriculture isn't limited to research labs. It's more accessible, explainable, and field ready as well. So as I was telling from start, it's the basic scanner that you're seeing over here. So one of the first challenges is this we was this one that we tackled. So how do we make high quality image acquisition affordable and kind of repeatable? So we tried with 8K image resolution cameras, multiple IR cameras and all these things, but none of those things actually worked in this situation, because we can't manage the lighting conditions, even creating some uh, photo shoot boxes or something of that sort, like the miniature versions. But even after trying out with multiple things of this sort, we aren't able to crack that code in terms of using a camera to capture these rice grain images. But so yeah, so the entire first thing that we the first challenge that came up is this one, to uh, which hardware setup to use for data acquisition in terms of getting the rice grain scans of 20 to 25 25 to 30 grams of rice grains. So instead of relying on industrial grade image systems that cover almost 1.5 lakhs, or let's say $2,000 kind of thing. So we used a standard flatbed scanner, which is just priced at 7,000 to 8,000 rupees, that is $100 actually. So even with this simple hardware, we achieved incredible detail, scanning at 600 dpi with a raw image dimensions of 1960 into 7015 pixels, which translates to nearly 8K resolution. And that's enough. Like that's enough for us to capture the granularity, to detect the tiny, visual cues like chalkiness, hairline fractures, or like subtle color distractions, discolorations, like that the rice grains will be having on them. So that are often kind of misread by the human eye, but this system will be able to capture those slight things as well. So the advantage is more of a twofold one. So first, the scanner provides consistent lighting and even the focus, unlike the camera setups that vary with ambient conditions stuff. And then on the second case, it ensures the repeatability across locations. So whether a mill in India or a lab in Bangkok, runs it, the input conditions remain standardized. So this decision anchors for the frugal philosophy of TrueRice, which is making the accessible hardware with the high fidelity and also scalability for any user environment as well. So as you can as I mentioned in the previous slide, that whatever the image resolution that we have captured from the scanner is about uh, 4960 into 7015 pixels, which is almost near to 8K resolution. So now we need to kind of build a image segmentation model to actually kind of uh, have the segment like the rice grain segmented from the amount of the scan that we actually got from the scanner that we are using. So from that scan image, I'll have to say I'll have to count the number of grains in that particular sample, which is around, let's say, like in terms of weight, it will be 20 to 30 grams kind of thing, which might be having like 1,000 rice grains. And I need to count those things with the AI over there. So the scan comes in, then okay, that is of as I was telling, like it's more of 4090, 4960 into 7015 pixels, which is like more of 8K resolution scans that we are getting out of it. So with that level of clarity, like with that level of resolution, and with that level of image size, which is almost like 10 MB image that is coming out of the every scan. So the challenge is the that most GPUs that we have now, the at least the consumer grade ones, are like, okay, now we have H100s and H200s kind of thing, but what about the consumer grade GPUs that we have now? So the challenge is they can't handle such large, high resolution, large images efficiently during the inference, not during the training. Training is one-time job that we do, but even during the inference, these systems cannot handle cannot handle such high resolution and the large images as well during the inference. So that's where the even kind of, let's say, okay, you are downsampling the image, let's say, from 4960 into 7015 pixels, which is 8K resolution. Like, let's say you are bringing it to 2K resolution. So maybe you're reducing the resolution using any of the online tools or something of that sort. Then the image will be getting blurred, right? Once you kind of start with decreasing the number of pixels, the image resolution decreases, and obviously the image gets blurred, and you can't even actually see if there is any black spot, or if the grains are broken or something of that sort. So that's the actual issue we have. So downsampling would lose the details in terms of whatever we can see on the grains, but keeping the resolution intact will the keeping the resolution intact will actually break the hardware. So that's where the SAHI, slicing aided hyper inference, comes in. So the model actually dynamically uh, slices each image into 1080 into 1080 pixel tiles. So whatever the image that you are seeing, like the 8K resolution image, which is 4060 into 7015 pixels, is sliced into 24 pixels, 24 tiles, uh, which are in the resolution of, let's say, 1080 into 1080. So with what are the slight overlaps? Okay, you might be asking me like, okay, the image that you are seeing over here, like if you kind of break it down into 24 pieces, how will how how they how we got it like this cleaned with all the there is no grains in the edges, and what about this thing? So I'll tell you what the image processing pipeline that we had for this, and yeah, we'll just like go to the next slide. But before that, yeah, the simple thing over here, the main challenge is to use this slicing aided hyper inference, which is coming in to help us slicing the each image, which is the 8K resolution image, into smaller tiles with the slight overlaps in between. If, when the tiles are which are getting cutted, there will be the grains. There are grains which are cutting in between the images as well. So this is their slight overlaps, runs the inference on each tile and then reconstructs the full result, basically using something called non-maximum suppression. So this slicing aided hyper inference is like a uh, key pre-processing technique that we use in terms of training our instance segmentation model. So as I was telling, once the tiles are splitted, which is into 24 tiles, so this will run the inference on those tiled images. So the even the whatever the model, like the instance segmentation model that is also trained, is also trained on these tiles. So we annotated these tiles, we trained the model on these tiles, and then the inference also happens on these tiles, and then they are stitched back. So they are reconstructed back into the full result, as you can see in the image, on the left side, over the full image of 8K resolution. So again, they are switched back to 8K resolution with all the uh, grains, detected with their proper instance segmentation boundaries as well. And this uses something called non-maximum suppression to eliminate the overlaps or the duplicate detections in between the multiple tiles that we that we kind of split it in between. So this approach gives us the best of the best of both the worlds, like in terms of the speed and the precision. So we can now detect very fine defects, even there is if there is any minor cracks, if there is any broken tip of the rice grain and all, we can easily detect with those things without even downsampling the original image. So essentially, it's it makes large scale inspection possible on a consumer grade GPU while maintaining the industrial grade accuracy. So it's one of the key reasons, why TrueRice actually achieves 97 to 99.5% accuracy with high throughput and zero dependency on heavy compute setups as well. So as I was telling, yeah, as you can see, this is a combined image of it's not stitched back, it just looks like so, but yeah, it's again the 24 tiles of the grains, which are actually cleaned on their edges. So as I was telling, uh, if you can see the left hand, the image on the left side over here, this is how a farmer or a miller will actually just put grains on the scanner, and once the scan is done, there will be the grains which are uh, got cut in between different the multiple tiles that you can see here, whatever the lining that you are seeing, there may be one grain which is in the first tile and which is in the second tile as well. So half of it will be in the first tile and half of it will be in the second tile. So when we train the model on such situations, the model will think, okay, this particular grain is broken. So in that way, there will be more broken grains in whatever the model that we are going to train. So to kind of resolve that issue, so we basically once we kind of uh, make those 24 tiles, then these 24 tiles of that particular scan goes into a tool called Gym. It's basically an open source Photoshop kind of thing. So we kind of erase those the grains which are in the edges of the image, which are overlapping between two different tiles, and we clean those grains in those images, and this is how the cleaned image, cleaned tile, tiles looks like. So these clean tiles will actually now get uploaded into Voxel 51's 51 platform, and on that we used automated annotation pipelines, which are built on segment anything model to actually kind of build our annotation for these rice grains. And this is how actually the tiles are annotated before we actually share kind of upload, uh, prepare our training data set. So this is how the annotations actually look like over here. So after, as I was telling, this is again the we we kind of classify, we kind of have the class distributions. We can see what type of grain that is, how many are broken, how is that the texture of that particular grain, how discolored is it, and all these things. And we'll see multiple kernels and all those things over here in this way. And then continuing with that, so we used this model called YOLO YOLO 11, which is like a nano segmentation model. As I was telling, our main concentration is more on this system has to be running more on the consumer grade GPUs, and one of that is the RTX 3090. So what of the even the training and also the inference that is going on now is also being run on this RTX 3090 GPUs. And even the model that we chose is also more of 2.9 million parameter model, and it's giving us best inference speed in terms of getting the accuracy. But obviously I was telling entirely the TrueRice product will be taking 30 seconds to give you the result. And why instance segmentation is more of, we don't want the bounding boxes for the rice grains. So this looks cool when the rice grains are kind of annotated this way with the instance segmentation with the proper boundaries. Actually, if they are bounding boxes, it doesn't look proper, and even we can't kind of measure the length of the grains, and we can't measure the length of the length and breadth of the grains as well. We do that we always have that. Okay, great. So before I wrap up, I'd like to take a moment to share a bit about where TrueRice was built, at Sustainable Living Lab or SL2. So SL2 is like a more of an ecosystem of organizations working across Asia, US, and beyond. And we are more focused on using technology, foresight, and grassroots engagement to tackle complex challenges in climate, sustainability, and digital transformation. And what makes SL2 unique is how it brings together innovation and inclusion, from building AI tools for farmers and the policymakers to enabling community-driven sustainability programs. So TrueRice is one such example, and a result of combining AI research, frugal design, and on-ground collaboration with millers, farmers, and policy institutions as well. So we have been fortunate to receive recognition for this work, including the India's first international agri hackathon, and multiple global AI initiatives. But what matters most is seeing these technologies reach people who usually get left behind the digital innovation. So let me ground this with a real world example. So our pilot with Raitang Organics, it's one of the Thailand's largest organic rice exporters. So before TrueRice, their grading process was fully manual, taking close to 4 hours per batch, and often producing inconsistent results, which when compared with other operators and batches. So this led to the quality disputes with the buyers, and this delaying the shipments, directly affecting the export timelines and stuff. So we bought in, we got in TrueRice over here, and now the things are much better for them in terms of the accuracy that the TrueRice is developing, and even in terms of the traceability that the TrueRice is giving to this client. And this is our journey in terms of whatever we have done from the last from the last 1 year, and we are almost scaling AI in agriculture, which is coming comes is coming from three major challenges, like which is data variability in terms of grain size, color, and all these things with different grains as well. That is where the cross crop adaptation and all these things is coming in. And even the regulatory standards, like regulatory standards in terms of FCI, USDA, and even Thailand export standards and all, like which we need to change, update on our site. So all these are there so that we kind of update them according to the client that are onboarded. So on the whole, TrueRice isn't just about automating the inspection. It's about making quality transparent, fast and accessible as well. It's like bringing together speed, objectivity, scalability, and also like empowering farmers, millers, and exporters to make faster and fairer decisions. So with that, I'll end my talk here. Thank you so much for listening through.